Hi students, glad to see you again. Well, today we are going to move on and start some really serious topics about algorithms. Okay, so the first topic is induction. Well, and you may say, why do we want to talk about induction? Because this belongs to some logical operating courses. Why do we want to need that? Why do we need that in the algorithm course? And the reason is in this course, we are going to prove some algorithm complexities in a really formal way. Well, if we want to have a feeling of something, and that's not hard, but if we want to do a formal definition step by step, and that will be much harder. And the induction is the basis of this part. And so how do we do induction? And let's suppose that we have a SK. And then Sk is true for a fixed constant k. And, well, let's say we start from 0. So the first step is we want to start from 0 and we want to prove that Sk is true when k equals 0. So this is the basis, that's the first step. So we show, well, we usually start from 0, but sometimes we may start from a different part. And say the first step, the basis, we show Sk is true when k is 0. Okay, and the next step, our goal is we want to show that if Sn is true, and then Sn plus 1 is also true for all the values n greater than k. If we have that, if we have a proof that showing Sn is true, so Sn plus 1 is also true. What do we have? Okay, we start from the 0. We prove that if for k is 0, S0 is true. And then we also have a proof here. So if Sn is true, we can prove Sn plus 1 is also true. What does this mean? This means we start from 0, S0 is true. And because S0 is true, we can say S1 is true. And because S1 is true, we can say S2 is true. And then we can go on and on forever. So this means for all the positive values, Sk is true as long as k is a positive value, right? So we are proving Sk is true. So this is the idea of induction. Okay, so well, this is a formal process of how do we do induction. So well, this is the claim we want to prove. Sn is true for all the values n greater than k. And the basis, we want to show a basis or a base case for a small number, for a really easy number that we can say, okay, starting from that part, and then for this value, for example, 0, Sn is true. That's the first step. The second step, we want to do an inductive hypothesis. And for the second step, we don't have to prove that's true, but we assume that for n, for the value n, Sn is true. So this is a hypothesis. We don't have to prove anything, but we want to put this hypothesis here. And based on this hypothesis, the step 3 is we want to start from Sn is true. We want to prove Sn plus 1 is true. Okay, so that's the 3 general steps for induction. So let's see example. Well, a very easy one. The sum from 1 to n is n multiplied by n plus 1 and divided by 2. Okay, so how do we prove that? We want to use those 3 steps for almost any induction. So the first step, the basis. So let's pick n from 0. So if n is 0, and then the sum from 0 to 0 is 0, right? But if we plug in n equals 0 to this formula, and then because it's 0 as well, this means, well, for n is 0, it is true. Or if you don't feel very comfortable with saying this, and how about you use 1 or use 2? It doesn't matter. You want to use a very small number and prove that it is true. And this proof should be really easy. You just plug in the number and then you can get it done. Okay, so the first step. The second step, the inductive hypothesis. Remember, for the second part, you don't want to prove that. You only want to assume that it's true. And what is that? So if we have n, for n, the sum from 1 to n is n multiplied by n plus 1 and divided by 2. So we assume that is true. And what's the next step? Based on Sn is true, which is the inductive hypothesis. The step 3, we want to prove that this is also true for n plus 1. So how do we do that? So we are summing from 1 to all the way down, all the way up to n, and then n plus 1. And what is that? So how about we put the first n items together, and that is the n multiplied by n plus 1 and divided by 2. Why? Because that is the inductive hypothesis. We assume that's true. That's the second step. And then the third step, we can use that. And then we add a n plus 1, and then using some tricky math, and then we can get it done, and eventually we want to get here. So eventually we want to stop here because, well, this part is n plus 1 multiplied by n plus 1 and plus 1 again divided by 2. What is that? That is Sn plus, right? So if you compare with this word with this word, what's the difference? Well, this n becomes n plus 1, this n becomes n plus 1. So if this statement, this formula is Sn, and what is this? This is Sn plus 1, right? So the general structure is, the first step, you want to find a base case. The step 2, you are assuming that Sn is true for n. And the third step, you want to prove that Sn plus 1 is true based on Sn is true. Okay, so let's see another example. This is the harder one. So a to 0 plus a to 1 plus a to 2 and plus a to n is a to n plus 1 minus 1 and divided by n minus 1. Okay, so what's the general process? The first step, you want to start from some really easy case, but you see, well, for all a not equals 1, so probably you want to start from, say, 0. Okay, so if we are doing the plugging in the 0 here, and then we can easily prove that it is true. So that's good. Well, this is the first step, and then the inductive hypothesis. Remember, this is part we don't want to prove. We just say we assume that is true for n. So that is, if you want to do the sum from a to 0, a to 1, and a to n is true. So the sum from a to 0 to a to n is a to n plus 1 minus 1, and then divided by a minus 1. So we assume this is true. And what's the next step? The next step is we want to show that it is also true for n plus 1. So we are using this part as the basis, and then we want to move on one more step, saying if we assume Sn is true, we can also prove Sn plus 1 is also true. So how do we do that? The process is similar because we are adding together a to 0, a to 1, a to 2, all the way up to a to n plus 1. Okay, but if you want to grab the first n items, that is a to 0 all the way to a to n, what is that? That's the inductive hypothesis, and that is this part, and then we are adding this together. So with some mathematical manipulation, and we can prove that that is also true for n plus 1. So how do we show that? So that part is a to n plus 1 and plus 1 again minus 1 divided by parentheses a minus 1. Okay, so what is that? If this part is Sn, now what is this part? This part is n plus 1. Sorry, it is if this part is Sn, this part is Sn plus 1. Okay, so from Sn we are able to prove Sn plus 1, and then our work is done because we have already showed the base case, and the base case is 0. So if 0 works, and then 1 works. If 1 works, 2 works, and if 2 works, 3 works. So we can go on and on and on, and we can prove that it works for all the way up to infinity. And this means Sn, the statement Sn is true. Okay, so this is the part for induction, and I'm going to stop the video here. So next video, we are going to start to talk about time complexity.